Okay, so welcome to Controls Lab. Cheers. Good to have you. So the idea with this is that it's obviously it's the practical component of 435, right? The idea with this lab is that we actually will be making a control system. I have my favorite toy in the world. One of my favorite toys in the world. Fresh from being worked on this past winter. Yes, this is what I do for fun when I'm not here. I build stuff to torture people with. I mean, to educate people with. I'm sorry. So this guy is kind of the coup de grace of what we're going to be doing in this class. It's a relatively simple system. We got a ping pong ball, have an infrared range finder, and there's a microcontroller underneath there that moves the servo to balance this ball anywhere that you want on that beam. That is the final project for this course, and it's going to be awesome.
We have to build one of those.
You have to program it.
Okay.
Yes. If you want to build it, I'm totally down with that too, as long as you also program.
Keep the program.
So that's where we're going. We're going to start off by talking about how to characterize a control system, what that looks like, what that looks like practically, all that. You'll probably be talking about a lot of it in class at the same time as well. So hopefully this will go together fairly well. We're going to do a little bit of simulation too. I have a Python script that goes along with that. So you're going to program your control system in using that. And then you can adapt it to the physical artifact. So especially because we only have one of those and there's like 6 of you. So we'll make that work. In terms of other stuff, I think that's about it. I think almost all of you are in classes from right now. My office is there, literally through the wall. I've moved since last fall. Haven't moved since last year. All my office hours are generally from 11 to 12. They are from 11 to 12, Monday through Friday. Look at my class schedule before you show up if you want to show up outside of those hours, because I have a crap ton of stuff going on. But it will be 11 to 12, Monday through Friday. Okay. Any questions before we get going? All right. So I know that Mr. Bolt has talked about his philosophy of control systems. So what do you know about control systems? What's your conception of them? What do they do? What's this class about from your point of view? Besides you taking a shower. Yeah.
There's always an input and an output.
Yep.
And there's stuff in between. It can change between like mechanical controls or like sensors and stuff.
Mm-hmm.
And is there always a feedback loop to it, or
there can be.
okay.
Yeah. Does have closed loop and open loop stuff. You guys will be talking about that soon. Any other thoughts? Those are all absolutely correct. Okay. So yeah, it's some system. Doesn't matter what it is. Be as simple as a guy in a shower with his hand on a hot water valve. This is a control system. You open the valve, go, oh crap, I'm burning my skin off, and then you close it, right? so which called you have which called that'd be a closed feedback system. There's some input to the system being you, the input being friggin' hot water. So you make some adjustment to the system, the valve, and it changes what the input is and so on and so forth. Yeah. It's a fairly straightforward thing. Your car, a cruise control, that's a control system, right? You set it at a certain speed and it adds power or lets you coast or uses engine braking or whatever in order to keep that speed, right? There's always but that's more formal control systems. Really, a control system could be as straightforward as a spring with a mass sitting on it. It's actually even better than that. I have this ball, I drop it, right? It's a system. There's input to the system, gravity, the system's response, it falls. And so on and so on and so forth. So you can explain anything using the control system model that you guys are going through in class. Here, we're going to focus less on like physics stuff, more so on the control side, like actually controlling stuff. So we'll have something like this, where you have some input like this would be someone reaching for the newspaper. The input it's that they're reaching him towards an article, and well, your eyes are keeping track of where your hand is relative to the thing. Say when you should close your hand, then eventually you'll grab it, right? So we're going to be a little bit more direct than this, but we're going to start off with something very, very, very simple. You guys ever looked? You guys ever seen the shock absorbers that are on your car?
Yes.
Okay, not everyone. Okay, cool. So let's pull up something here. I have one, but they're really heavy. I helped someone install some new shocks on. I think it was what was it? It was a Mustang, and there's no way I could compress the springs on this. So you get what you get. Okay, so this is a shock absorber for a car. It's a pretty standard gig. Sort of two of the same thing, pretty much. So this kind of epitomizes a lot of what our control systems do. So in order to explain that, let's go through the points. So you have what's this called? My goodness. If you have a shock, actually, you know what? I'll just draw it on top. On top of that will make life a lot easier. So we got a spring. Obviously, we have a mass. That's what it's attached at the top here. The bottom's just attached to your wheel, or whatever. Let's see if I can draw that by hand. So you have a mass up here. Note that you will need to know all these terms at some point. So if you want to take notes, go for it. But I'll leave it up to you. So you have a mass, you have a spring, and the last part here is what's called a damper. Have you guys talked about that in class? Those terms sound familiar. Yes. Okay. So what's a damper? Go for it. What's a damper?
I mean, we haven't really talked about them in like a spring sense, but like a dash pod or something
Okay.
could be an example of one that kind of like slows down acceleration of it.
Yes, yes. And it does it in a very particular way, right? What does a dash pot react to?
Isn't it like the viscosity of like the oil or like the is it viscosity or friction? I don't know.
They refer to the same thing.
Yeah.
Yeah. Yes. And so when we look at this, it's called a damper or a dash pot, it'll provide some resisting from force that's usually proportional by some constant to the speed at which the dash pot's being extended, right, or compressed. And it's always going to resist whatever that motion is. Yeah, absolutely. So we have some velocity dependent force there. It's like friction, except it's proportional to velocity. It's not constant. It's not constant. Great. The mass is pretty self-explanatory. It's a mass. The spring is pretty self-explanatory. It's distributing the load, right? It's resisting based on how far your extent. So if you purely had a spring, you just be bouncing, and you went over a bump, you just keep bouncing forever if there was no friction, right? So if you just had a spring, you had like a plot of like oscillations versus time, it would just always look like that. So the function of the damper is to kind of slow that down and go from a pure sine to bring that down to zero, right? It's like your car doesn't do that forever. So let's start with let's start with trying to characterize how that response looks like, or what that response looks like. So if I see my mouse, no, we don't want that. Good. Mouse. Okay. Not that one. That one. Okay. So if we want to start quantifying how a system responds, this is going to be our first stop. So y-axis is amplitude of the oscillation, t is time. In this particular case, 1. Hey, come back here. 1, which call our spring mass damper system that we have here, is trying to control the oscillation so that it'll settle down at whatever length 1 is. We'll say that that's the typical height of the car. It's trying to settle it out so it's back where it should. It should be. You guys heard the term rise time, overshoot settling time? Okay, cool. So these are different things different parameters that we're going to use to characterize our control system. So if I had a car go over a bump and I look at how it oscillates, this is how we're going to measure that. So the first one, this is TR. This is called rise. This is called rise time. Rise time is the amount of time that it takes for the system to go from 10% of its steady state value, 1 being the steady state value, to 90% of the steady state value. So amount of time that it takes to go through that change based on where it started. That's the system's rise time. A faster rise time, the faster you pop up. So if you had a control system and you wanted to act fast, you wanted a really, really short rise time, right? would that be a good thing or a bad thing for, say, like a car going over a bump? If it goes over the bump, the whole car rises up a bit, and then the springs and the shocks try to pull it back down as quickly as possible. Would that be a good thing or a bad thing? Why?
Your car would probably bottom out.
Yeah, well, that and your head would probably hit off of the ceiling of the car, right?
Yeah.
Yeah. So having a very fast a very quickly responding system is not necessarily a good thing. Hence why we want to characterize it. The thing that's going to make your car bottom out is this guy, though. This is the maximum overshoot. So if my steady state value is 1, question is, how far above that does the vehicle go or the system go as it tries to hit the steady state value? It's usually on the first oscillation, if it's a stable system. That's of concern because, well, yeah, if even if it slowly starts to correct the car, if it goes past that middle point and starts sinking into the shocks because the springs are so soft and it hits the ground, that's not any good either. Yeah, cool. Next, it's called also knowing when that's going to occur is important. That's this TP, or the peak time. So you got peak time, rise time, max overshoot. Max overshoot is a actual dimension or value. It's not a time. Rise time, peak time obviously are. TS is our settling time. So it's the amount of time for the system to come within a certain set of limits. It's typically accepted as being within 5% of the steady state value. Question is, when can you do that, right? Because like obviously it's within that here and over here, but it goes outside of those bounds until here. So the settling times, essentially the last time that the system enters that band of plus or minus 5% from the steady state value. Sound good? Any questions on that? Great. All right, good, because this is what you're gonna be figuring out for your lab this week. Let me back up a second. So what we're going to do this week is apply these to a simulated spring mass damper system. So a spring with a mass on it and a damper attached to it can be modeled using this equation here. If you have not seen dots before, like this, they just indicate derivatives with respect to time. So x dot would be the derivative of x with respect to time. X double dot would be the second derivative of x with respect to time. So x dot is velocity, x double dot is acceleration. So in a spring mass damper system, the general equation is this: mx double dot plus bx dot plus kx equals 0. K is the spring constant. B is it's a measure of the measure of the damper, how strong that is, and m is the system's mass, its inertia. So you might think that the higher the system's inertia is, the more it's going to try to ignore the spring. The stronger the spring is, the kind of stiffer that the system's going to be, and so on and so forth. So we can make a couple of these into non-dimensional variables that help us comprehend the system more. One of them is natural frequency. So that's this omega n. It's defined as square root of k over m. Essentially, it's if you didn't have a damper in there, this would be the frequency at which the system accepts energy readily. If you want an example of what that looks like, my favorite one would be something like this. Second. So this is an example of the wings of an aircraft reaching their natural frequency. They're accepting, and they're accepting the energy that the forces that are being applied to them are at the exact same, being applied at the exact same frequency that the structure can best accept them. So the wings do stuff you don't think that they ever should be doing, and they shouldn't be doing. This is why if you look at an aircraft's manual, it's something called a never exceed speed. This is what happens when you go over the never exceed speed, and then the wings go up and fall off the plane. It's a bad day. So that's an example of what happens when you're at your natural frequency. If you've ever heard of the Tacoma Narrows Bridge, that was someone else that was excited at its natural frequency. The structure started moving based on the winds in such a way that it would continually accept more and more energy. In other words, natural frequencies are how you get things to accept energy very, very fast, sometimes with very, very bad results if you don't plan it right. So that's what a natural frequency. So that's one of the reasons why we care about natural frequencies. You can also do a whole lot of stuff with them. David Bolt loves talking about them. I was talking about them. You can actually do everything you do in mechanics of materials, you can do in terms of natural frequencies. It's really cool. It's super cool. It's so freaking awesome. Anyhow, if you ever go into helicopters, that's what matters. Like you'll spend like untold hours characterizing the natural frequencies of your blades, because if you don't, it's a bad day. Anyhow, so that's that. Next thing is damping ratio. So this is a squiggly dude here, a zeta. That is your damping ratio. We use damping ratio instead of that B term because it's a heck of a lot easier to understand. So an undamped system has a damping ratio of 0. And that would be this, that would lead to this kind of response here, where it's just the same sort of oscillation, same amplitude for all time. There's no damping to it. It's never going to calm down. It's always going to continue at its same rate. If you have a damping ratio with a value of between 0 and 1, you have what's called an underdamped system. So the steady state value for this system is, wow, I can't draw a straight line, is somewhere around there. So the system goes up, misses it, catches itself, comes back, and just kind of bounces around for a little while. Most systems are underdamped, like cars. They're made to be underdamped a little, just a little bit. They're not as bad as this, but they kind of bounce around a little bit. If you've been over a pretty big hump, you felt that, where it goes up, comes back, and then it kind of settles out. It doesn't take long, but it's underdamped. The next step up is when zeta equals 1, you have a critically damped system. You'll note there's no overshoot here. It goes pretty much straight to the steady state value, done. If you have a zeta over 1, you have an overdamped system. So you see that this guy, it's the same idea as the critically damped one, goes straight to the steady state value. But what's different about it? What's different about the rise the rise time?
Takes longer.
Yeah, it takes long. You might think of this as somewhere where the dash pot's been cranked way up. So it's coming, so it can't move very fast. So it just kind of, so it can't overshoot, but it can't move very fast. So it's just slowly sliding into where it should be. As opposed to when you have it tuned just right and this goes, woof, done. you usually don't want a critically damped system or an over damped system because it moves either too slow or just very, very quickly moves to the final result. Having an under damped system usually decreases the stresses on your your components or your passengers. Let's all work out as well. But yeah, I think that's all the terminology that we need. Any questions on those? Great. So let's get to it. If you want to pull up Excel, we're going to code up a simulator for a spring mass damper system, and your job, whether you choose to accept it or not, is to find the rise time. I'm going to write this down somewhere. It's to find the rise time, max overshoot, peak time, and settling time. Rise time, peak time, max overshoot, and settling time for a set of 5 spring mass damper systems. These systems are going to start at what's called a hold. They're essentially going to be a spring that's been pulled, and you let it go and see what happens to it. So there's going to be some differences in how far you pull it down and also how fast it's traveling when you let it go. Like if you throw it as you let it go. All right, cool. So, but first things first, we have to create this system. So what I would like you to do is, it'd be nice if this was, okay, stop doing that. Nice if this should that. So I want you to make a few annotations on the left hand side here for mass, spring constant, natural frequency, damping ratio, initial velocity, initial position, and damped natural frequency. So mass, I just arbitrarily put it in as 0.2 kilos. Spring constant as 100 newtons per meter. Zeta, this is one that you'll be changing. This is the damping ratio, right? B naught, this is one that you'll be changing. It's arbitrarily set as 0 meters per second, right? For now, should say there's no dimension on zeta. And X naught, this is one that you'll be changing. It's in meters. So let's make sure we get all these computed right. So natural frequency, that's the square root of also put all the equations here. That's the square root of your spring constant divided by your mass. So make sure you got that computed. Zeta's input said the damped natural frequency is your natural frequency times the square root of 1 minus zeta squared.
What's that one again?
That is your damped natural frequency.
What was the equation for?
Your natural frequency times the square root of 1 minus zeta squared.
What's the natural frequency? Sorry.
Square root of K over M.
Okay.
It's spring constant divided by mass. So does everyone have those
What's the damped one? Sorry.
natural frequency times square root 1 minus zeta squared?
Okay.
That one. Something like it. Cool beats. One got stuff. All right. So, note the difference with the natural frequency and the damped natural frequency and the regular natural frequency. Damping moves the natural frequency. You can see that in how omega n and the damped omega n are different from one another, right? It changes how the system can accept energy. And if I had a critically damped system, the damped omega n would be 0, right? You wouldn't be able to destabilize the system by adding energy at a certain rate, right? That's why critical damping is kind of an interesting thing, or why damping is a big deal. So you can move natural frequencies around in order to accommodate whatever you're trying to do. If you want an example of that, you can think of a helicopter. You're spinning a rotor at a certain speed, right? So it's going around like say it makes one revolution per like 100th of a second. So it's a 100 hertz rate of rotation. Now your rotor is pushing air down onto your tail boom, say. So if you have a 3-bladed helicopter, say a 4-bladed helicopter, 4 times per revolution, your tail boom is going to feel whoomph, 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 right? It's going to get hit 4 times per revolution with a burst of air. So it's being pushed at a rate of 400 hertz. So if it is a natural frequency of 400 hertz, the tail boom is just going to start bumping up and down until it probably moves far enough that it actually hits something. So if that was a problem for you, you'd have to add some form of mechanical damping to your tail boom, or make it stiffer or something, so that its natural frequency wasn't at 400 hertz. Does that make sense? Okay, cool, sweet. So we got all that. Great. Now, but for the rest of this. So this graph here on the right, that's what you guys are trying to make. And then your work for lab, and pretty much until next week. You don't have to do it now if you don't want to, because you have everything here that you need for it. Promise we'll be doing more physical things as we go on. Your work for next week is to find those 4 characteristics that I mentioned earlier for a set of different parameters I'll give you as you start to get the model together. So spring mass dampers are kind of nice because we have an analytic solution for them. In other words, I can just type a thing into Excel and it can figure out how the thing is going to move. I've made up a whole bunch of times. You probably want to use time steps of around like 5,000ths of a second or less in order to model this thing. So just as a hint. In terms of what the equation is, here you go. So x of t, that's the actual location of the pen of the end of the end of the pen of the end of the pendulum of the end of the spring. That's what we're trying to track. That's what we're going to be finding the rise time and all that of. Essentially, it's going to be trying to go to 0 from wherever the starting location is. It's going to try to go to 0. So the steady state value for every single case is going to be 0. All right, cool. When we go to solve this equation, you have to calculate A and phi for each, for each case. A is the maximum amplitude of the system, and phi is a phase offset. So you have to compute those, stick them into x of t, and then solve that for every single time step that you simulate for. You should simulate until you reach the settling time of the system. All right. Any questions?
This is on Canvas.
This newest, I just edited this today. I'll put it up there very shortly.
Thank you.
Yep. But that's the gig for today. I'll have an assignment with the different combinations of zeta and zeta, x naught, and v naught up for you shortly. Until then, you can get this guy set up and ready to run. Any questions? All right, game on. So